Good morning, everyone. I'm glad to be here with you today to share what we are doing at Tinyclues. Who am I? Mathieu Despriee. I'm engineering manager, so at Tinyclues, in charge especially of machine learning scalability and operability. So, who is Tinyclues? Tinyclues is a SaaS company, a French SaaS company in marketing technology. We are using deep learning for campaign targeting and planning. The company has been founded in 2010 by mathematicians, and we are using deep learning since then, so before it was cool. So the product is designed for marketing teams, and we try to rethink the way they work. So instead of them trying to figure out the segments to talk to for each of their campaigns, or manually configuring groups and flows and rules and in their emailing software, we let them focus on their true job, which is working on their marketing strategy and their communication. So we propose them to define the topics they want to talk about and their business goals, such as improving the revenue per sent mail or promoting a new category in the product catalog, for example, and so on. And artificial intelligence do the rest to find the right audience and to avoid spam. So it's working well. Usually our customers are doing A/B tests against us, and we are proud to have that kind of figures when it comes to revenue improvement. And in general, it also means less email sent, less spam. And we are quite proud of having that working. So how it works? So our clients are retailers, e-commerce companies, travel companies, and so on. And they provide us with their data about their customers, the products, the purchases, events such as clicks and page views. We only take first-party data with opt-in, and most of the time the data is anonymized. And we process that data with a lot of Spark pipelines to clean it up and make it converge into a common internal data model that will be then fed into our predictive technology. So it's mainly composed of two phases. The first phase of unsupervised learning, where we try to model two things. The first thing is the interests of customers, and the second thing is the topics, that is what the marketers want to talk about. Could be a product category, could be a brand in their product catalog, could be anything, or a new product is going out. And from that, we build more traditional supervised learning, doing some prediction. And the prediction actually is just a function of the customer and the topic. And given the user, the marketer's input about the topic you want to talk about and the business goals, we can build the right audience and prepare files they can use in their emailing software or Facebook or a mobile push notification. If we are lucky enough, we also have tracking activated on these channels, and we can use that as a feedback loop to constantly improve our models. So let's focus a bit more on this predictive architecture. So again, we start from this common data model. So this is relational data, and believe me, it's certainly not as simple as feeding 2D images like in deep learning tutorials, like very nice squares. It's much more complicated than that. A very particular thing is that we also have very sparse data. We have a typical product catalog is 10,000 to 100,000 products with new products every day, niche products, low activity customers, The data is always dirty. Even if we have some Spark pipelines to clean it up, it's always dirty. And we decided to live with that and to build model from that point. So the first phase is a very classical encoding one. So we have one-hot encoders, a top, feature hashers, and so on, that produce sparse features that are then fed to a multi-layer system of unsupervised learning. So clearly, this is where the magic happens. We are very proud of this element. This is where we build meaningful representation of data about customers, about topics, even if the data is dirty or anonymized. And the output of this is embeddings, that is a sparse or dense feature that we then store in a feature bank that we will use later in our pipeline. Then come a very important phase, which is sequence learning, which is how we can make sense of event history. We're going to talk about that in a minute. And then the last phase is the more classical one of supervised models with probability of clicks, probability of purchase, revenue expectations, and there are kind of very classical logistic and so on. The models here are typically very wide. We always have at least 10,000 column wide models, so it's that's why they are so powerful. So let's back to the sequence learning. This phase is under active research at Tinyclues, because making sense of history is not trivial at all. And also, it's computationally intensive, so we try to improve that. And we can start from looking at what are the events. So events are page views and clicks and so on. And they are particular objects in the sense that they are not always meaningful individually, but when we look at the full sequence, they are. They are obviously time-ordered, okay, and they are not independent from each other. And a technical element is that they are not all the sequences from the various customers are not of the same length. So we have to find algorithms that can make sense of that. So there exists a model architecture working with that. It's RNNs, Recurrent Neural Networks. Do some of you know that kind of architecture? Not so much. So RNNs are neural networks with loops in them, like this. And this loop is allow information to persist in them. I prefer showing them this way. They are enrolled. That is, all the time steps. The time steps are presented flattened. So we can feed such a network just by flattening all the history for a given customer, for example, and feeding all that at once to have a prediction about this particular customer. They allow input sequence of variable lengths. You just need to pad the past with zeros and organize your network to discard this data. You can build networks by stacking several RNNs, if you will, but just a layer can start memorizing things from the past and giving some insights about that. So there are many class of algorithm inside the RNNs, inside the group of RNNs, and we are going to talk about the LSTM, long short-term memory. They are very popular these days. That's because the initial RNNs that were invented in the 80s, I think, they have a problem. They can't learn long-term dependencies. They tend to lose memory at some point because of the backward propagation or the optimization. they tend to lose memory, if you will, and they don't keep things in memory for a long time. And LSTM were invented exactly for this, to avoid this problem in '97. Today there are many variants of LSTM, and they are widely used, especially in speech recognition, translation. They are used as building blocks of assistance, and they have great results. So let's dive in and look at an LSTM. So this is an LSTM network. So don't get too frightened by this diagram. It's not that hard to understand, actually. So you can see all the different cells that are unrolled along time. And you can see two horizontal lines that are crossing and passing from a cell to the next one. If you look at the top one, this is the memory, the cell state. And the cell state is going all the way down from step 0 to step n, unchanged, almost unchanged. And this is this line that will keep memory. The rest of the cell is just gates that will control how the memory changes given an input. And from an input and the current memory, how we're going to produce an output. So they are not so complex to understand, and they are working very well. We can build a model to predict purchases, for example, using LSTM. I will show you a quite simplified example. So if we start from event history of a customer, so events again are page views and clicks. We need to pad them to a max sequence length, and then we are going to pass them through an embedding layer. So embedding is just a vectorial representation with a meaningful, yes, with some meaning attached. And then we can feed that into an LSTM. So each time step of the LSTM is going to produce an output. And we are going to predict only one thing. This customer is going to purchase or not, so we need some form of aggregation. So this is a very classical pooling mechanism that we can find in neural networks. So we can use a sum or a mean or a max or whatever. And we will find very classical, fully connected dense layer in the end towards the logistic, for example, to predict a purchase. That kind of network would work, probably, but it would not be very specific in a sense that if we're interested in learning the probability, the interest in some product, this network will not give that. So we need to bring some kind of focus. We need to teach the network to focus on specific elements for what we're looking for. This is the idea of attention models that we can add to that kind of architecture. So attention models are a way to make the network focus on element of interest. In fact, we start again with the event history, and we add the notion of query. In our context, it's a topic. Also a product category, a brand. And we go through the same kind of embedding. And after the LSTM learning from the event history, we are going to use that to modulate the LSTM output. So the attention network is by a simple multiplication. So imagine that you have a topic, which is a vector with to make it simple, 0 and 1s. The zeros will cancel out the element from LSTM output that are not relevant, and the 1 will keep that. And we just need to make a form of aggregation. This is a softmax, and the output of that is weights that we are going to use to modulate the LSTM output. So this way, we have a weighted and interpreted history of the event of this customer given a particular topic. So the topic for this customer, for example, or for this prediction. So the rest is we can feed that in the final layers of the network. So we gave a try to this type of architecture. And for the implementation and execution, we wanted to find a technology to be easily distributable with Spark, callable from Scala because all of our pipelines, Spark pipelines, are in Scala. Of course, keeping some interoperability with Python because it's what is used in our lab, with a high performance out of the box. That is to say that it should benefit from the native libs that we can have or platform-specific libs that we can have, and the ability to use the GPU for training purposes. And last but not least, a good support of sparse tensors or sparse matrices, because it's maybe not very visible in that architecture, but in most of our architecture, we have a lot of sparse vectors, and we need a good technology to handle that. So we gave a try to MixNet. MixNet is a deep learning framework incubated at Apache. Its backend is in C++. It has multiple front-end languages, including Scala. And it has a very good integration with linear algebra native libraries, including Intel MKL. So MKL is a library provided by Intel that leverage all the platform-specific or Intel processor instruction for maths and computation. The published benchmarks with GPU are very good for MixNet. And also, it aims at interoperability with other frameworks such as Keras and PyTorch and so on through the Onyx standard. So we tried to implement the network I shown, the LSTM with attention. So we started from Python side, as we are in the lab. So the code is not very readable, but it's actually quite easy. You just declare the various layers of your network, and then you declare the forward pass, that is how you're going to go from a layer to the next one. You declare all of this, and MixNet takes care of computing the backward pass for the gradient descent, and to compute the whole, to prepare the whole computation graph in a symbolic model that can be reused. And actually, that's the case. Reusing it in Scala is as simple as this. So we can export, with one line in Python, we can export the model, and reusing it in Scala is not more complicated. We just need to load the symbol, that is the graph, computation graph, and the parameters of the network, and feed that to the good API, and feed the data to get the predictions. Sorry. And using that from Spark was not much more complicated. So you just need to make your model and parameters available to workers first through HDFS or broadcasting, and do the work inside the map partition, data frame or RDD map partition. And inside this map partition, you initialize your model once, so you load the models and prepare the parameters and so on once, and then you can feed the data to it. There is just some data manipulation to do, because you are grouping all the rows into mini batches to benefit from the vectorized implementation of the backend. So you are stacking all your rows, convert that into arrays, ND array, that's the name of arrays in MixNet. You feed that into to the backend through ND arrays, run the prediction, get back a matrix that you unstack to get the output rows. So it works well. You have to pay attention to resource usage on the workers, of course, because you need to make sure that the backend in C++ will have enough CPU and RAM because it's not visible from Yarn and Spark. So you need to make sure that enough resources are available. You need to pay attention to data copy operation that will happen between the Spark vectors that are in Java memory and MixNet, which is in C++ backend. So to share a bit some learnings about MixNet in Scala with you. So clearly the library is very young, so it has some youngness issues, such as mixed API styles or the Scala API that is lagging Python's one. Sometimes you have unhelpful error message coming back from the backend. You have to live with that. It's a bit tough sometimes. Sometimes you also have some non-trivial boilerplate code to write because it's still under heavy construction. And unfortunately, the Onyx interoperability has still limitation as of today. Yet, we found it very promising and very fast out of the box. Many binaries are directly available with hardware optimization and native implementation, and usable from Scala Spark pipelines, as you saw. A few takeaways to conclude. So to find the tiny clues within your data, you need powerful learning algorithm to discover the latent meaning. That's what we are doing in the unsupervised learning. Regarding event history, LSTM with attention models are especially good. And using inference model from a Scala Spark code is easy and performant with MixNet, even if this framework has still a lot of limitation. And that's it. Thank you.
Thank you, Mathieu. We have ample time for a few questions, so the floor is open.
Hello, Mathieu. Thanks for the presentation. Question. So actually, the fact that you use Spark was mainly just to broadcast the model and kind of reproduce this behavior of a load balancer, which will just balance the work to the workers so basically, I mean, what I understand is why to reproduce this architecture with Spark, whereas we know that it is possible to do it with Python and any kind of cluster with Kubernetes or anything else. Did you try? And I'm very curious to see why. Is it because you wanted to have it included in your pre-processing pipeline, or?
A good question. Actually, what we are trying to do is to improve the integration here. So the output here is so it's producing files, but there are a lot of Spark jobs here. This schema is a bit simplified, and so here we have a lot of Spark, and we try to improve the integration here. In the future, we would like to have a more end-to-end integration between Spark and the processing. Especially when it comes to this part of sequence learning here. We are dealing with event history, and you can see that as a very big join with each of your users. So you have your user and all the history they have, and the join is the best thing I know to do join is Spark. For that volume. So we would like to bring all this processing closer to the Spark jobs to benefit from Parquet, from join optimization, and so on.
Hi, great presentation. So one question I had regarding the event history, like how do you prepare your data? So is it just a case of like aggregated by a customer at a daily level or hourly level, or is it just a case of like a customer group by day or date, something like that?
The typical depth of data we use for each customer is like 1 year. So we get 1 year of events. But this year is not starting at the same point in time for each end user, for each customer. Maybe a very recent customer on the website has this year starting just now. And maybe you want to catch also a past customer that didn't go to your website since 6 months. So the past year is shifted. So it's a kind of join with some complication to have the right window of data for each end user.
Here. So a great presentation, thank you. About the attention model, you mentioned that you take the events history of the users and the topic of the user, or the topic of what, and where this comes from. Is it topic modeling, or this is a given a fact, and how it's combined in the attention model?
Topic is much more an input from the marketers. It's what you want to talk about. You want to talk about a part of his catalog, the new iPhone coming out, or whatever. So it decides what you want to talk about, is product groups or something. And we try to make sense of these arbitrary groups of products or of categories or labels. We try to make sense of these groups here in unsupervised learning, and we build embeddings and vectors that represent that topic, and we use that in the learning.
Hi, thank you. I noticed you were using Scala and Spark for prediction, but Python for training, and maybe not Spark for training. So my question was, would you like to use Scala for training and not Python, or do you want to use Python for training? And if you do not use Spark for training, that means that all your training data fit in one single machine, but your prediction data fit in, you use Spark, so it's on many machines, so you use less data for training than for prediction. It's strange, no?
Good question. So the division is not train versus predict. It's much more lab versus production, in a sense that in the lab, our data scientists are constantly using many deep learning frameworks. They are testing many things. We have also a lot of proprietary libraries and frameworks that are similar to scikit, if you will, that are in Python. So in the lab, it's definitely Python. But one thing is that our models need to be constantly refreshed. We retrain them all the time. They may be trained once in the lab, but when we are happy with that, when they are stabilized, we retrain them all the time constantly. So we need to train them in production as well. And we don't need to have the same infrastructure in lab and in prod. It could be easier, but in the same, Scala, Spark has some virtue. We are happy with that in production. So that's what we are trying. I agree with you, it's not that easy to mix all those technologies, but that's what we are trying to do.
Okay, that's all the time we have. Let's give it up for Mathieu one more time.